All right, guys, let's talk just a little bit more about graphs. Earlier on, we were introduced to our displacement time, our dt, and our velocity time, our vt graphs. So I introduced these when we were looking at these equations of motion. And to talk just a little bit more about those, briefly, what we do know is that for a displacement time graph, for a dt graph, we know that the slope is the velocity. And we know that, let's just call that a 1. And we know that curves are acceleration. And so if we were looking at a displacement time graph where we had some high velocity of an object that slows with time to 0, then it would look something like this. And so this would be an example of positive velocity with negative acceleration. And whenever we see curves on a dt graph, we're not going to be asked for the acceleration at some specific point in time. Uh, let's say that at t equals 2 seconds, and we were wondering, well, what's the velocity at that point? Well, we won't be doing that because that's a derivative. So we know that we would actually be taking a limit um, of delta x with respect to delta t as t approaches 0. And so we won't be doing any of that. But what we could do with curved sections is if we had the initial beginning of the time period and the ending of the time period, let's call it t and t naught, we might be asked for the average velocity, in which case a straight line that connects our beginning and ending point. Well, the slope of that line is the average velocity. We might be asked that, but we wouldn't be asked for the instantaneous acceleration. That is velocity. The instantaneous velocity at some specific point in time. We won't deal with that. Remember, we're only dealing with averages. So if you're asked to calculate the slope at any specific point in time, it's going to be on a segment of the graph that has a straight line. And then we can probably deal with that. And what we remember for the velocity time graphs, the VT graphs, is that the slope is acceleration, and that the area is the displacement, and it's a good idea to know that curves, since the slope is the acceleration, curves are non-uniform acceleration. In other words, the acceleration is changing, which, if you remember, requires a little bit of calculus. So if we had a velocity time graph and there are curves on this thing, you're not going to be asked for the instantaneous acceleration, the acceleration at some specific point in time. But you may be asked for an average, in which case, of course, it's the same story. All right, this would be the average acceleration, that dotted line there from your t0 to t naught. We might be asked that, but we wouldn't be asked a specific, what is the acceleration at this point in time? That one's a derivative, and we won't be doing that. And likewise, since the area is the acceleration, if it's a curved section, you won't be asked for the the displacement. If the area is the displacement, you won't be asked that um, because that one's an integral, and you would integrate the equation of that line. Well, that's calculus. Remember, this is algebra and trig, so we won't be doing that. If you're asked for a displacement, it will be on a part of the graph that has a straight line, and you can figure out the area by adding up, rectangles, squares, and triangles. Um, so the one thing that I want to add to this, and then we're going to take a look at a bunch of these in our homework, um, is that if we want to represent motion in the negative direction, so for a single dimension, right, positive is one way and negative is the other. So say for instance we had an elevator, and we call the upward direction positive and the downward direction negative. Then the elevator can move up and down. We want to be able to look at it in both directions. So when we do this, we will draw a graph that looks like this with our horizontal axis in the center. So if you'll look, position, that's displacement. Um, this is a DT graph, but this one allows for motion in the positive direction and in the negative direction, displacement in the positive and the negative direction. So if we look at this graph, this is an example of, say, an elevator that starts at any given floor, and maybe the floors are 5 meters apart. So this elevator moves with constant velocity to 10 seconds, and it is displaced 5 meters. So it went up a floor, and then it stayed at that floor because this section here is at rest, right? The slope is the velocity on a DT graph. So this has no slope, it is at rest. It stayed in one place at a displacement of 5 meters for 20 seconds, from 10 to 30 seconds. Then it began to move in the negative direction. So this positive slope, that's positive velocity. This negative slope, that's negative velocity. And it passes the floor that it began with at about 40 seconds here. And it continues downward to negative 10. So it went down 2 floors from its starting point, down 3 floors from when it was at rest. And then again, it is at rest. So in the entire scenario, in the first 10 seconds, the elevator went 5 meters up, then it stopped for 20 seconds, then it went 15 meters down, right? It went from positive 5 to negative 10, and then it stopped again. So we see that on the top part of the graph, we have in the first section here, that's positive velocity. In the second section here, it's at rest. In this third little piece here, it has negative velocity. Here it's back to where it began. Then it continues with negative velocity in the negative direction. Now we are in negative displacement. We've gone below where we started. That continues for an additional 20 seconds. And then at t equals 60 seconds, we are 10 meters below. Now, this is an example of how we deal with positive and negative direction. And with these graphs, it is extraordinarily useful to be able to relate a DT graph and what is going on there to a velocity time graph. So if we look down here, that dt graph at the top, let's do a velocity time graph below it that matches it. Now, this is what is the slope, because this vertical axis is velocity, and we know that on the first graph, the slope is the velocity. So if I look in this first section here, for the first 10 seconds on the dt graph here, it was a rise of 5 and a run of 10. That's 5 meters over 10 seconds. That's 1/2 meter per second, and it is positive. So for 10 seconds, the velocity is positive 10 meters per second. And then it is at rest. That velocity is 0. And it stays there till 30 seconds. So here between 10 and 30, it's at rest. And then the velocity, if we check this slope here, I believe we'll find that it is negative 1/2 meter per second. And that is from 30 seconds to 60 seconds. So negative 1/2 from 30 to 60. And then we are back at rest for the last 20 seconds or so. So here, for those of you who are into calculus, this one's the derivative of the first graph. For those of us that aren't into that yet, it doesn't really matter. I hope you can see how this velocity graph on the bottom, this VT graph, aligns with the DT graph above. Right? The DT graph above tells us the velocity, the slope is the velocity, and we translated that onto our velocity time graph at the bottom. Now, if I wanted the displacement, which is the area on a VT graph, I have two areas here. I have area 1, which is in the positive direction, and I have down here area 2, which is in the negative direction. So what is the displacement of this elevator after all of this time? Well, it went 5 meters up and it went 10 meters down. And we know that the area is the displacement. So this first one, area 1, that's positive displacement. Area 2, that's negative displacement. And all I need to do for the total displacement of the elevator is to add these two. Assuming area 2 is negative. If you're, surely you'll call that a negative. At any rate, the difference between the magnitudes of the two, with the direction of the displacement being the greater of the two. So hopefully we see how that works. Now, please remember the unrealistic aspect of these graphs for algebra is that we're not looking at curves, right? So the elevator and now this is my little Walmart version of my graph here. Pretend that's perfectly straight. In the Walmart version of this, the velocity doesn't really start from rest. It curves upwards to some velocity, and then it slows down to rest. And so these areas where there are curves, these little places where it curves, we won't be dealing with those. And if we do see them, we won't be asked specifically about a point within those. We might be asked to generalize, we might be asked for averages, but we will not be asked to specifically solve for the slope at some point on this curve. And with that, we should have enough to be able to delve deeply into these. So we're going to look at these today with quite a few practice problems. The multiple choice. All right, that does it.